Hi everybody, let's think about distributed torque problem. In this problem we have a cantilever beam. Cantilever beam is located like this. At one end is free, but other hand is fixed to the wall, firmly fixed to the wall, And of course we have some diameter d and length is L, and one different thing is we have distributed torque. The intensity is 2100 Newton meter per meter. This one is constant intensity T per unit length, unit distance. Of course, we have some length L is given, and some shear modulus of elasticity is 80 gigapascal. And polar moment of inertia, in this case, be careful about the unit. Normally, so far we had the unit is millimeter exponential 4. In this case, we have meter, which is expressed in meter. That's different. When you calculate the final value, you must convert this unit to appropriate unit. And here we would like to find the strain energy by distributed load, strain energy. So far we considered about the strain energy. Strain energy, U is what? U is calculated by, with this formula, 2G polar moment, shear modulus of elasticity, and IP, polar moment of inertia, and T, torque squared, and L. This one is so-called strain energy for concentrated torque. But in this problem, we have distributed torque like this one. And this distributed torque is evenly distributed. And we can take this one, small infinitesimal one, which locates x distance from right side, and we will consider this one, the small element. When I draw this small element is like this one. Okay, it's very small cylinder, very small cylindrical type, which inside is full. Its length is, we can say, its length is dx. And some torque is acting like this one. Acting torque, when you apply the right hand side rule like this one, then this kind of torque, T is acting. And here as well. And when you consider just T, which just for unit distance or unit length, then this length is T, maybe dx or something in total. Okay, anyway, when you consider very small infinitesimal one, this T for unit length, but on the right side is totally summed. On the right side, totally summed, are acting like this one. Tx is acting, which is when you think it's isolated system, then total Tx, this distance, total torsion is acting on this part. You can imagine. If it is in the state of equilibrium, same torque is acting in this side as well. Okay, when you understand it properly, it is kind of a mechanism, then we are ready to apply this formula there. Okay, we can substitute its values. For example, Tx is acting instead of large T, torque is acting there, and length is dx, and 2g shear modulus of elasticity is given like that, and ip polar moment of inertia. When we assume the diameter is d, then polar moment of inertia can be easily calculated. ip equals 5 over 32 d4. When you apply this kind of formula, you can calculate easily. Okay. And here, the cross-section area itself is not changing. The only changing things is this kind of distributed torque. Okay. Now we would like to calculate this value. Strain energy U equals, when you apply this one to G, IP equals 5 over 32 D4. And T value, what's the T value? TX squared. Length is dx. Okay. When you take a sum from 0 to L, this value is what? Strain energy for this system. Here we have a very relatively simple value, because 2g, all those things are what? Is constant. Even t itself is constant. Then we can easily take the integral value. Finally, when you take some integral, then you can calculate some value. It's like this one. And this value is written what? The unit is what? Joule per, not joule, Newton meter, then it is expressed in joule. Because this one is what? Strain energy. Okay. In this case, we dealt with to find strain energy for total system. And when you calculate final value, you can substitute all values to there. Then finally you can calculate which is expressed in joule. When you substitute your values to here, to there, then maybe this kind of gigapascal, just the only thing to have some considering point. Otherwise meter or pascal, you can easily substitute everything there. Then you can calculate finally the value. Okay, in this example, we have calculated strain energy. Okay, this is strain energy. The strain energy is normally calculated with this kind of formula. In this case, concentrated torque case, you can apply this formula. But here, in this system, it's not the concentrated one, it's distributed one. Okay. Then we introduced a small infinitesimal one element, and dx, and maybe this one is diameter is d, and acting torque is tx. Then when you apply this one to this formula, then when you take integral, then you can find finally strain energy for this example. Okay, now let's think about another example. In this example, we have a tapered bar. This one is tapered bar. With a tapered bar, the slope angle is relatively small. The slope angle. This angle is very this angle. I mean, this angle is very small. That's the basic assumption. Otherwise, when the slope is very large, then we cannot apply this kind of approach. Maybe later on, when slope is very large, later on when you study more about mechanics of materials, you can have another approach to solve this kind of problem. Okay, anyway, at the moment we assume tapered bar. And another assumption is maybe material itself is homogeneous material we have. Normally we introduce this kind of homogeneous assumption because it's much easier to deal with problem related to material itself. Next, the cantilever beam, the cantilever is attached to the wall firmly at point D. On left side, torque T is applied like this one. And by the torque, this cantilever is changing elastically. Then we can apply some related torsional characteristics can be applied to this problem. Okay, rest of them dimension L is given like this one, and diameter on the left side is dA, on the right side dB we have. And we would like to know when you apply this kind of torque, eventually on the left side some change of angle can be happen. And we would like to know the change of angle in this case. Tapered bar we assume, and change of angle is very small, and the material itself is very homogeneous, it's uniform, and otherwise its dimension is given. In order to solve this kind of problem, you can think of a strain energy. Applied strain energy and work by torque T is the same as stored strain energy. At first, stored strain energy work during by torque is 1/2 T phi A. Okay, phi A. This one is work by torque T. Work is of course given in joule, in the form of joule, right? This one is the same as strain energy. And we would like to find the strain energy in this case. Okay, in order to find that, we assume we introduce very small infinitesimal one. We take this one, very small one. Thickness is dx. Maybe this one is cross section is a circle, and this is very thin disc, if you want. And this diameter is dx. Okay, here externally torque T is acting like this one, and if it is in the state of equilibrium, T is also existing like this one. Okay, that's it. Then we can calculate for stored energy, stored strain energy for these cases. And another thing is torque T is the same, but diameter dx is changed. Dx is what? Sorry, not dx. Cross-sectional area A is changed. Cross-sectional area is phi and and 4. This cross section is changed. Or this dx this dx is changed. When you think of area, then you can use this one, but mainly this dx is changed. That's key point. Okay, anyway, when you calculate the strain energy in this case, strain energy U equals to G. Let's assume the shear modulus of elasticity is G. IP. In this case, IP equals IP. When we think of this location is X, IP X, let's say IPX. In this case, IPX, because it's changing. IP X equals 5 over 32 diameter dx 4. You can say like that, this one. GIP, dx is changed. Here, dx is changed. And next, t squared is constant, it's not changing. And its length is what? Dx. Okay, then we can take integral from 0 to L. From x is changed 0 to L, this distance. Then eventually strain energy can be calculated, and this strain energy is same as the work by external torque T. Okay, problem is here. We can substitute this IPX value to there. But trouble is inside we have dx value. Dx value is changed. How we can calculate dx? Okay, I will draw this one again. Okay, on the right side is dB. On the left side, this length is d what? A. And this length is what? Let's say L. Okay, somewhere here, we introduce X. And its diameter is what? Diameter is dx. We would like to know dx. And when you extend this one, then draw again. When you extend this one again, then okay, let's think of this length is LA. And finally, LB is this distance LA plus L. Then we can have some relationship, similarity relationship we can introduce. When you consider this triangle and this triangle, you can compare both of them. Or you can compare both this one. Okay, let's consider this one, dA over LA equals what? When you consider this triangle, and when you consider this triangle, then dx over LA plus this distance is what? X. By applying similarity relationships, we can have this kind of equation. And trouble is here, we must eliminate LA. And how we can eliminate LA value? Of course, LA, LB has this kind of relationship. But we can apply another relationship between small, this one, and larger one. Or we can do that. dB over dA equals dB over dA equals L plus LA, sorry, LA, L plus LA, L plus LA, L plus LA, this distance, and divided by LA. Okay. When you substitute, you can find LA value here, independent upon LB or another one. Then you can substitute there. Then you can finally get dx. This kind of process is one method. Another simpler one is you can think of another simpler one. Just we draw a line here, this line, and you introduce this line, which is parallel to this line. Okay, and this line. When you think of inside this triangle, and we can say we can think of the dimension. When you consider this one, this triangle, let's say its location is x, and here end of this point, let's say L. This length is dB minus dA because we consider this length, and this one is what? Dx minus dA. Then we can have much easier to calculate the relationship between dx and any other one. This one is dx, this length. Okay. Then we can introduce x over L equals dx minus dA, and here dB minus dA. dxL, dx minus dA, and dB minus dA. Then finally we can calculate dx value. Dx, this one, equals like this one. Dx equals dB minus dA is multiplied by this value, x over L plus dA. This value is what? dx. Okay, by drawing this line, we can have this relationship xL, and we have some similarity relationship between larger triangle and smaller triangle. Then we can introduce the relationship here. Then finally we can find the dx. Okay, here we found dx. We found the dx value. This dx can be substituted there. Okay, and if we substitute, then finally we can have IPX. IPX is there, and T is constant to G. G is what? Shear modulus of elasticity is constant. Then finally we get this kind of integral. What does that mean physically? We consider just a small infinitesimal one, this one, but we sum everything from here to there with a small, disk. We add up, and we summed up from left side to right side. Then finally we have strain energy. We can calculate like this one. Okay, in order to calculate strain energy 2gipx t squared x, which is applied to this one, then we require IPX is required, IPX polar moment of inertia at this point is required, and here dx is unknown. Then we have some relationship between triangle, and we draw a line here, and when you apply similarity relationship between small and large triangles, then you can find the dx value. When you substitute dx value there, then finally you can get strain energy. When you calculate strain energy, then strain energy is the same. Of course, this one is also expressed in joule, and when both values are equal, then finally you can get the change of rotation, change of angle, phi a, you can calculate. That's the 4 tapered cantilever